Okay, so how is everyone today? Good, I hope. Okay, so last time we were talking about relations and functions, and we're still talking about relations and functions. So you can look at the notes for the definition of a relation, but here I'll draw a specific one. Again, a relation is a collection of two sets called domain and range and a mapping between them. So just to give a specific example, I'll say that the domain contains 1, 2, and 3, and the range contains, 5, 6, 7, 8, and 9. So now we have two sets, but in order to be a relation, there needs to be a mapping between them, and I'll define it like this. So the existence of those two arrows, the way you read that aloud is that 1 maps to 7 and 1 maps to 9. Here I'll say what 2 does. So I'll leave 2 like that. So 2 maps to 5. And I'll say that 3 maps to 9. Like that. That'll be good. Why not? So this is an example of a relation. So I could ask, well, what's 1 related to? 7 and 9. I could ask, what things are related to 9? 1 and 3, etc. But we're really not going to talk too much about relations. So in the end, I'll just make the following observation, is that to be a relation, it must be the case that every element in the domain has at least 1 arrow leaving. So, well, how many arrows are leaving 1? 2, and then there's 1 leaving 2 and 1 leaving 3. As a result, this is a relation, and I'd also like to point out that there is no restriction. So no restrictions of any kind on the range. So that's what it means to be a relation. But in fact, in our class, we are interested only in a specific kind of relation. The specific kind of relation that we're interested in is called a function. Can you remember what makes a relation a function? So I think you might be saying it right, but because English is kind of clumsy, what you said might be ambiguous. So I'll give an example of a function. So here's an example of a function. Okay, so this one is a function. So to make it clear, I'm going to start writing the constraint and ask you to finish the sentence. So every element in the domain has, and then now how do I finish this sentence?
An arrow leaving it? 1 arrow.
Exactly 1 arrow, right? So not at least 1, but exactly 1. As a result, this first thing that I wrote, this relation, is this relation a function? It is not. Why is this relation not a function? Right. There's 2 arrows leaving 1. So as a result, this is not a function. This is a relation. Is this relation a function? Yeah, because notice every element in the domain has exactly 1 arrow leaving. Now, for the rest of the day, we're going to make a vending machine analogy. So I hope everyone knows what a vending machine is, right? In fact, I think there's one right over there. I'm talking about the things where you go in and press. You have a look. There's glass. You see the yummy things that you might want, or I think we also have like vending machines for test booklets and things like that. But let's ignore that because that's not exciting. Let's think that there's candy bars in there. So a vending machine is you can look and see the choices, and then you insert money and press a button and you get your thing. So we're going to make it more simple. In fact, that there's no money required. You just see the thing, press the button. All right. So the kind of vending machine that we're talking about is the kind of vending machine that when you press a button, 1 item comes out. Right, like a normal vending machine. It's an error. It's an error in a vending machine if you press a button and 2 items come out. Right, that's an error. So in that analogy, for this vending machine, if you were to press button 3, what would come out? A 9. Good. But what if you were to press button 1? Right, it would item 7 and item 9 would come out. So that's not right. That's not the kind of thing we're talking about. Notice that every button, when you press it, just 1 item comes out. But there is something that's a little bit disturbing about it, and that is that well, there's a 6 in there, but what? There's no button to get it, but it's still a vending machine. But it's just like one that's like taunting you, right? Oh, I wanted that 6. Okay, so again, there's no restriction on the range. No restriction on the range. Another kind of funny thing about this particular vending machine is that what if you wanted to get a 7? Yeah, and that's kind of weird too, isn't it? You could press button 1 or you could press button 3, but that's still okay. But we want to have, we want to talk about the kinds of vending machines where it doesn't have those problems that we were talking about. But in every case, when you press a button, only 1 item is permitted to come out. So this is a continuation of that page. So 3. We went on last time to be specific and talk about a specific kind of function, which we'll call surjective. So here is such an example of a surjective function. So 1, 2, 3, and 4 in the domain, and in the range 7, 8, 9. So now I'll say what button gives you what. So 1 to 9, 2 to 7, 3 to 8. And now notice that because there's more buttons than items, and every button must do something, that means that I have to connect button 4 to something that's already there. So I'll just do that for lack of a better choice. So can someone remind us what surjective means? Right. So if you look on the previous page, a relation is such a thing. A function is when you have a restriction on the domain. Exactly one arrow can leave, which means in vending machine parlance, every button has to have exactly one function, one item. Here, now we have a restriction on the range. So every element in the range has at least one arrow. Arriving. So, how many arrows arrive at 7? 1. How many arrive at 8? 2 and 1. Okay, so then this function that we wrote is surjective. To make a vending machine analogy, this is the kind of vending machine that when you walk up to it, every single visible item, there's a button you could press to get it. But what else might be true?
2 rows of Snickers.
Right. There might be more than one way to get the item. So for example, if you wanted a 7, there's just one way. You have to press button 2. But if you wanted to get an 8, well, you could press button 3 or button 4, in fact. Okay, good. Next, we went on to say another kind of word, another word which meant a different kind of thing. That word was injective. So can you remember what that one meant?
Only one? Or at most one?
At most one. So again, to give an example, maybe the domain is 1, 2, 3, and the range contains 6, 7, 8, 9. So now where vending machines are concerned, notice the kind of problem that there is, that there's 4 different kinds of items in the machine, but
3 button choices.
only 3 buttons, right? So evidently one of the kinds of candy bars is not reachable. Okay, so suppose that this is the mapping. In fact, at most 3, right? Because, I mean, you can imagine a kind of vending machine that's got, like every delicious kind of candy bar that exists, but it also has a lot of broccoli in it. And in fact, every button gives you a broccoli, right? Oh, we don't like that. Okay, so what's the restriction now? So every element in the range has, and then how do we say this? At most one. Okay. Good. So at most 1 arrow arriving. That means what are the permitted number of arrows that can arrive?
0.
Or
1.
1. That's it, right? So how many ways are there to get a 6? 1. That's
Wait,
it.
aren't there 2 ways to get a 6?
Mm,
Oh, I guess I meant hypothetically, there could be no arrows going there or 1 arrow going there. But you're saying here you can only push a 2 to get the 6. I'm sorry.
Right, right. And then how many ways are there to get a 7? 0. Okay. And then for an 8, there's 1 way, and for a 9, there's 1 way. Do you agree that for every item in the vending machine, there's either 1 button or no button? As a result, this is injective. Now, is this surjective? No. Why is this not surjective? You can't get a 7, right? It's not possible to get a 7. fine. So this one is not surjective. Is this one injective?
No.
No.
No, because 8 has 2 arrows.
Right, because there's more than one way to get an 8. So you can one notable thing in the end, these things are what controls the definition. But a good way to sort of look at it and see is that, well, notice that there's 4 buttons, but only 3 kinds of candy bars. And because every button has to produce something, that means that at least one candy bar must be producible in 2 ways. But we could redo it and make all of them give you a 7 so that you couldn't get an 8 or a 9. Okay, fine. But similarly, other things for here. So then the kind of, to make a vending machine analogy, again, this vending machine, because it's injective, you could put it in a room that only one person could get into at a time. And if you knew exactly the way the vending machine worked, that means that you could inspect the person as they come out and see what they got, and you'd know what button they pressed. As a result, for example, if someone walks out of the room holding an 8, then what button did they press? A 1. There's no way they could have pressed anything else. Whereas if you put this vending machine in the locked room and they walked out with an 8, would you know for sure, uniquely, which button they pressed? You would not. Similarly, if this vending machine were in a locked room, there'd be no way for them to walk out with a 7. Or, to say it in a funny way, if they did walk out with a 7, you know that they didn't press a button. They used a baseball bat, right? Or a rock, right? Good. So it's possible for a function to be both of these. What's the name for being both of these? Bijective.
There's why it's bi, because it's both of those.
Because it's both of them. So domain. So let's say that I put 3 buttons, 1, 2, and 3. And if I want it to be bijective, then how many items can be in the vending machine? 3. Because to be injective, there has to be at least 3 items. And to be surjective, there has to be at most 3 items, because otherwise it wouldn't work. So suppose that this is the mapping. So now the restriction is that every element in the range has, and then now, so for surjective, we wrote at least 1 arrow arriving. For injective, we said at most 1 arrow arriving. So for bijective, how do we say it? Exactly 1. Because it has to be both of these, right? Because, well, if you say something like, I'm thinking of a number that's at least 10, and another hint is that it's at most 10. Can you guess my number? 10, right? So has exactly 1 arrow arriving. And to make yet another vending machine analogy, a bijective vending machine is the kind of vending machine that when you walk up to it and have a look at the items, the choices, every single choice there is a button you could press. And furthermore, for every single choice there is only 1 button that you could press. Good. So like this kind of vending machine, in this case, it is injective like that one. So if someone walked out with a 7, you'd know for certain that they had press button 2. Any question about these? Okay. So, an example. Suppose that this is the domain. So the domain is, say, 1, 2, 3, and 4, and the range contains 6, 7, 8, and 9. So, because the number of items in the range is the same as the number of items in the domain, in principle, we could go on to write a mapping that's bijective. But I'm not going to do that. Okay. Now, to make it possible for us to talk about this efficiently, instead of referring to this as just the function, and it doesn't have a name, I'm going to give it a name. So I'm going to wrap it up in all a nice box. I'm going to write its name on it. I'm going to call it f. So now the function is called f. So the first request I could make of you is please evaluate f at 1. So that's how you say it in English. Then the way you write it in math language is like this: f and then open parentheses 1. So what is f evaluated at 1? So the question in plain language is, what is the output corresponding to input 1? So what comes out? An 8. Okay, then now that we've done one of them so thoroughly, I could ask a different one. So how about f evaluated at 3? What's that? 7. Okay, good. How about 2? Please solve. F of x equal to 9 for x. A 2 or 4, right? So again, to render this question into English, you could say what input x produces output 9. What button would you have to press? Well, as y'all said, button 2 or button 4.
Now, am I to not get that f confused with function?
It is a function.
Is that why it's named f?
No.
Okay.
Well, and yes. Let's be clear. So the reason why I wrote f, and the reason why in textbooks very often functions are written as f, is because function starts with f. But when you're writing a real variable, usually you write x. But not every variable needs to be named x, right? And not every function needs to be named f. And similar. Okay, so there's 2 ways to get a 9. As a result, we can say something about this f. We can say something that it is not. What is this f not? I agree, but even before that.
Also not surjective.
X is not 1 or 3.
Okay, so I mean, just as a result of what we've written here, I mean, it's not injective, right? So therefore, we could say that f is not injective. not injective, because an injective function must have at most one solution. So the purpose of this page is I want to start bringing out the idea of equations. So just like for vending machines, if it is the case for every item there's at most one button you can press to get it, then that vending machine is injective. But if there's an item where you could press 2 or 4 to get it, then that vending machine is not injective. Yes?
Okay, so, I mean, because when I look at the definition of surjective, it says has at least one arrow. Every element in the range has at least one arrow arriving. You're not saying that's not true. You're just saying what can you deduce from the information we learned in number 2.
Right. Right. So now here's a different question, which I suspect you're expecting. Now please solve f of x equal to 6 for x. There's no solution. Again, to make the vending machine analogy, it's asking, what button do you press so that you can get a 6? Well, there's not a button that you can press. As a result of just the things in item, just the stuff in item 3, what can we say about f, in particular, what it isn't?
Now we can say it's not surjective.
It's not surjective. Okay. Any question about this? So we can say what it's not, right? Okay, let's have another one. What if this is the function? So how about 1, 2, 3, and 4 are in the domain, and the range contains 7, 8, and 9. And suppose furthermore that we call this function h for no good reason, just to call it h. Now before I draw the mapping, the arrows, you should be able to tell me right now something that this function is not. It's not bijective for sure, and that means that it's not one. It's not which one? Not injective. It couldn't possibly be. Why could it not possibly be injective?
Because if there are 4 values in the domain, then and it is actually correctly named domain.
Yeah.
It
Right.
has to be
We can be at least
2 arrows going to one of the range numbers.
Very good. So I'll do that. So I'll say 1 goes to 9, 2 goes to 7, 3 goes to 8, and now I managed up to now to make every button have a unique one, but now you can see that now that we're going to wire up button 4, something has to be repeated. So I'll do that. As a result, I can ask the following question. I could say, well, please evaluate h evaluated at 4. So what is it? It's 7. Okay. 2. Is it the case, does every h of x equal to 7, h of x equal to 8, and h of x equal to 9. So does every one of those have at least one solution? Yes. So, for example, how many solutions does that one have? 2. So that one has 2. How many does this one have? Just 1. And that one has 1. So is it the case that they all have at least 1? Yes. Therefore, we can cover up the picture, and I can tell you that because this list contains every element in the range, and because you're telling me that every one of those equations has at least one solution, then you can tell me something about H. Therefore, H is surjective. A surjective vending machine is a vending machine where you look at it and every single item can be obtained by pressing a button. A surjective function is a function when you try to solve an equation and every equation has a solution, but it might have more than one. Do you have a question or you have a stretch? Yeah? Uh-huh. Yeah, I'm just drawing arrows.
So like, I don't know, like I've seen a test or something like it just comes up with random.
Yeah. Yeah.
Okay, I'm confused with something.
Oh well, it'll get complicated. I'm keeping us in a little place, a garden, before we move on. You got to learn how to juggle like 3 balls before you move on to 4, right? Does every h of x equal 7, h of x equal 8, h of x equal 9? And so again, this is an exhaustive list of every element in the range. Does every one of those have at most one solution? No, right? Because, well, you can see that 7 has 2 solutions, which is more than 1. So the answer is no. And you could say, for example, f of x equal to 7 has 2 solutions. As a result of, we could cover up everything except what we have written in item 3, and we can make a conclusion about H. What conclusion can we make? Therefore, it is not injective. That means, well, injective applies. Injective is, in a sense, what it means to a mathematician is that existence implies uniqueness, right? So, so you could say it like this. Here's something that wouldn't work out good. We could say something like, okay, we're gonna meet. I've got a treasure chest full of $1 million. For you, and I want you to meet me in the Walmart that's in the Dallas-Fort Worth area. Now this is a problem, right? Because on the one hand, you really want the money, but on the other hand, you have no idea what I'm talking. You're not sure uniquely which one I'm talking about. Okay. Good. So any questions about those things? Yes?
I'm not quite sure how that little anecdote relates to what we just did.
Not sure. Well, it would be like, let me say it like this. Here's a game. This is the vending machine. Suppose that we come to a game, and I say, okay, here's the game. I want you to. I'm thinking of an item to get out of the vending machine, and if you tell me the right button, then I'll give you $1 million. But if you tell me the wrong button, you give me $1 million, or even $1, whatever you like. So that doesn't sound like a very good game, because if I'm in control of choosing the one over here, then that means that I'll win, right? Because if I say I'm thinking I want item 9, what button am I thinking of? 1. There couldn't be any other button. But if I say I want item 7, what button am I thinking of? Well, then you've just got a 50-50 chance, right? So injective means that there's just one answer. Surjective means that there is an answer, but there might be more than one answer. Good. So now, in our class...
Can I ask a quick question?
Yes.
Before you drew the arrows, how did you know that was not bijective? That's the part where I'm confused.
Because...
I understand, like, once you draw the arrows and everything after, but that first question that you asked,
right.
I'm clueless. I don't understand.
Okay.
How everybody figured that out.
Let's say it. Okay. So the name of it is called the Pigeon hole principle. So and the way it's usually said is like this. But let's not do it with pigeons. Let's do it with candy bars. Suppose that we have 3 boxes. And suppose further that we have 4 candy bars. And suppose further that every candy bar must be placed in a box. So you know, you've got 3 slots. And we've got a red candy bar, and a green candy bar, and a blue one, and a black one. So where do you want me to put the red one? Okay. Where do you want me to put the green one? Second one. The blue one? Third one. And now here's the thing. There's one more candy bar. Is the black one? Where do you want me to put it? Okay. Now, can you agree to the following? That no matter what sequence of you telling me where to go, it had to be the case that at least one of the boxes had to contain at least 2 candy bars. So, there's 4 buttons. There's 3 items available in the vending machine. Every button must vend something. Therefore, for one of the things that could be vended, there must be at least 2 buttons that go to it. That's why. Similarly, if we turn it around, if we turn the thing around, like this one, there's 3 buttons, but there's 4 items in the vending machine. As a result, one of the items cannot be obtained. And in this particular example, it just so happened to be 7. So does that answer it?
Yes.
Good. Other questions? Okay. So in Math 1314, the most common kind of function is a function defined by an expression.
How do you feel about the abbreviation FXN? Sorry for
Oh, that's fine by me. Okay, so let's have an example of what that means. Well, I could say let f of x equal x squared with domain uh, 3 to 10 and range the reals. So now there's no more arrows, right? We're not doing the arrow thingy anymore. The first question I could ask is please evaluate f at 5. So what I mean by that in plain language is I want you to substitute substitute x equal 5 into x squared, and then tell me what that value is. 25. So f of 5 is 25. Okay, great. So now that we did one sort of super overbearingly, I'll ask a different one. So about f evaluated at 8. 64. Okay, no surprises, I think. F evaluated at 8 is 64. What about f evaluated at 2? No. I disagree.
Oh, it's not on the domain.
It's not in the domain, right? So this is undefined. It's undefined because 2 is not in the domain. All right. So to make a vending machine analogy, again, that would be like if this was the vending machine and I said, could you please go over to the vending machine and press button number 12. Right? There is no button 12. Okay, so then it's not a thing. Similar here, right? There is no button 2. There isn't one. All right. 4, I could say, well, how about please solve f of x equal to 49 for x.
It's 7.
Why 7?
F of x squared.
Mm-hmm.
X 7 into 7 is
Square root of
it's
49.
7 the whole square. So
Oh.
x is
Okay. So you're telling me that when you square 7, you get 49.
yeah.
Okay. But wait a minute. I think if you square negative 7, you get 49, right?
It's not in the
Oh, right. So,
Saying to me that the domain is 3 to 10 because it definitely didn't occur to me.
okay. But what I want to point out is that, so do we agree that when you square negative 7, you get 49, and when you square 7, you get 49? However, this one is not a solution. This one is not a solution. Why not?
Because it's not in the domain.
Because it's
Which is why
not in the
I
domain.
said.
Good. Well, I have to bring it. I have to, even if you don't take the
Oh, no, I
the
would-
detour,
I definitely did take the detour.
I still have to make us take the detour so no one gets trapped there. So that one's not in the domain. This one is a solution. Okay. Good. Fine. So here's another question. So how about so I'll preface this by saying I wouldn't ask this question. How do I want to say it? No, I would ask this question. Never mind. I would. I surely would. Solve solve f of x is equal to 144. 144.
No answer. Undefined.
It's not that it's not that it's undefined. It's not that there's no answer.
We don't know the domain.
It's
We do
not-
know the domain.
It's not in the domain. The answer is undefined.
So there's no solution.
No solution. Yeah.
Right. As a new, it's well, no, it's the same f.
Yeah, that's what I'm saying. I'm sorry. This isn't a new problem. Is what I was saying.
Right. Yeah. Okay. So then, well, can we agree that the only real numbers that square to 144, the only choices are negative 12 and positive 12? Okay. And then of those choices, which ones are in the domain? Neither. Neither. However you say it, I'm not sure. So not that one and not that one. Therefore, there's no solution. There's no solution. Therefore, as a result of that, you can say something about f. You can say something that f isn't. Therefore, f is not.
Greater than 10?
These are the buttons. Those are the candy bars.
So it can't be 0.
Inject.
It's not. It's not.
Inject.
It can every candy bar be achieved?
No.
No, right? Because
Injective.
it's not surjective.
Yes.
Therefore, f is not surjective. Right? This is like a this is like a vending machine where you walk up to it and every conceivable item is in there. Right? But actually, there's not enough buttons at all to reach them. Any question about this? Yes?
So one is two undefined, and then this one is like number three. The one with two.
Okay, it's because if you like it like this, x equal to 2, right? That's what we're asking about, is not in the domain. It's not a button. It's not an input that's permissible to provide. So here's a different question. So I need a different f, a different function to, I think, fully show what you are requesting to see. So how about we say that h of x is equal to 5x plus 4 on the interval 2 to 10. So that is to say, that's its domain, with range the reals. All right. So now, what if I say, please evaluate h at 8? Then in the first place, we need to ask ourselves, is that even defined? Is there even a button 8? How can you tell that there is a button 8? Because it's in the domain, right? It's among the permissible inputs. So because it is in the domain, that means that now you take that 8 and you evaluate it in that expression, and you get 44. So that means that what that means is that 8 is in 2 to 10, and 5 times 8 plus 4 is 44. Second question. What if I request of you, please evaluate h at 20?
There's no solution to that.
It's not that there's no solution. It's that it's not in the domain. The input is not in the domain. It's not among the buttons.
So you say not possible.
Not defined. So this is not defined. Is not defined, or is undefined. It's not defined because 8 is not in 2 to 10. Thank you. Yes. So now the question that you asked, I need to ask 2 more questions to get the point clear. Please solve h of x equal to 5x plus 4. No, that's its definition. Please solve that equal to 19 for x. Well, that means that you could solve it algebraically like this. 5x plus 4 is 19. You can move the 4 over so that you'd have 5x is 15, and then divide by the 5 and get this, x equal to 3. So is there a is that a solution? Yes. That's a solution because why? Right, and 3 is in 2 to 10. So that's a solution. Finally, I could say, please solve h of x equal to 9 for x. And then you could do it in exactly the same way. 5 times x plus 4 is 9. So 5 times x is 5. So x is 1. But what? But 1 is not in the domain. So there's no solution. Did that answer it? Hopefully.
Yes, thank you.
Okay, good. Yes?
In the previous page,
Uh-huh.
why is it not surjective? Because surjective says that the range should have at least one arrow pointing towards itself.
Well, the range is the reals. So this is all the available candy bars. Do you agree that 144 is in there?
Yeah,
Is there a button you can press to get it?
I agree. From the domain.
Not in the domain. No, there's not. There's the only buttons that would get there is if there was a button 12 or a button negative 12. But there isn't. So you could think of it like this function doesn't cover all possibilities. Good. So I hope you all have a nice weekend.